Hi, good day everyone. I am Gerald Debron with Cherry Manuel Pasayluon, and we are your presenters for today. And we are going to discuss the basics of finite geometry. Finite geometry started when mathematicians and geometers followed the axiomatic systems in the late 1800s. It was developed while attempting to prove the properties of consistency, independence, and completeness of an axiomatic system. Geometers wanted models that fulfilled specific axioms. Often, the models found had finitely many points, which contributed to the name of this branch of geometry. Finite geometry is any geometric system that has only a finite number of points. Finite means limited or fixed. When confined to a plane, all finite geometries are either projective plane geometries with no parallel lines or affine plane geometries with parallel lines. Fano, who lived in 1871 to 1952. He was born in January 5, 1871 at Mantua, Italy. He is credited with being the first person to explore finite geometries beginning in 1892. He is also best known as the founder of the finite geometry. His first work in this new geometry included 15 points, 35 lines, and 15 planes, all in a three-dimensional plane. As the father of finite geometry, there are records about him that his expository memory on continuous groups and geometric classification published in Encyclopädie der Mathematische Wissenschaft. Fano's contributions to Lie theory are described by Armand Borel in his historical essay on Lie groups. He also wrote a book with the subtitle Geometric Introduction to General Relativity that connects geometry and physics. And also, in 1892, a famous model of projective plane named today the Fano plane is in particular constructed. Fano originally studied a three-dimensional geometry, but the cross-section formed by a plane passing through his configuration yields a plane finite geometry. Here are the 5 axioms for Fano's geometry. Axiom 1. There exists at least one line. Axiom 2. Every line of the geometry has exactly 3 points on it. 3. Not all points of the geometry are on the same line. 4. For two distinct points, there exists only one line on both of them. And 5. Each two lines has at least one point in common. For this geometry of Fano, point and line are undefined. As in previous finite geometries, the meaning of on in the axioms is left to the intuition. In finite geometries, as well as in ordinary Euclidean geometry, various expressions can be used for the same idea. For example, all of these state the same relationship, that a point is on a line. The line contains the point, and the line goes through the point. These axioms resulted to the following theorem. The first theorem is Theorem 1.7, which state that each two lines have exactly one point in common, which is taken from Axiom 5. In geometry of Fano, the number of points and lines is more difficult to guess. Try to guess before reading the development leading to the next theorem. In Axioms 1 and 2, there exists at least one line on it. 2. Every line of the geometry has exactly 3 points on it. There are at least 3 points in the geometry based on Axioms 1 and 2, while from Axiom 3, not all points of the geometry are on the same line. This gives us an idea that there is at least a fourth point, as symbolized in figure 1.6a. In Axioms 4, states that for two distinct points, there exists only one line on both of them. This only means that there must be lines joining this fourth point and each of the existing points, and creating another points to make the line with 3 points. This makes our figure 1.6b. And by Axioms 4 and 5, there must be line joining points 1, 6, 7, points 3, 6, and 5, and a line joining points 5 to 7. And this form our figure 1.6c. Thus, Fano's geometry contains at least 7 points and 7 lines. 1, 2, 3, 4, 5, 6, 7 points. 1, 2, 3, 4, 5, 6, 7 lines. Let us assume that there is an 8th point and consider, for example, as shown in figure 1.7 on the left, the intersection of the line passing through points 1 and 8 and the line 3, 7, and 4. Axiom 5 requires that line 1, 8, and 3, 7, and 4 have point 3, 7, or 4, since that would violate Axiom 4. That for two distinct points, there exists exactly one line on both of them. Thus, it must be in 9 point, but that violates Axiom 2, which states that every line of the geometry has exactly 3 points on it. So, the assumption of an 8th point has led to a contradiction and must be rejected. The next theorem is Theorem 1.8, states that Fano's geometry consists of exactly 7 points and 7 lines. Let's consider a rewriting of the set of axioms for Fano's geometry, with the word point replaced by student and the word line by committee. A table may be used to represent this finite system. For example, Table 1.1 shows committees in vertical columns. Substitution of numbers for the student names would show that Fano's geometry itself could be represented by the same sort of table. You should be able to set up a correspondence between each column on this table and each line in figure 1.6c, noting that the students can be matched in alphabetical order with the points in numerical order, as it is shown here. The connections between the theory of combinations and the number points and lines in finite geometries are profitable to explore. For example, it might appear at first glance that a quick way to determine the number of lines in Fano's geometry would be to count all possible combinations of 7 things taken 3 at a time, since each line has 3 points. But there are 35 combinations of 7 things taken 3 at a time, and there are only 7 lines in the geometry. So a study of figure 1.7 will make it possible to reconcile this difference. Consider points 1 and 5 and the line they determine. There are 5 other possible points to form lines, and all of these possibilities are counted in the 35. But only one of these points, point 4, is actually on the line through points 1 and 5. Hence, only 1 over 5 of the actual number of possibilities result in lines. Since 35 over 5 equals 7, there are total of 7 lines. Further insights can be gained by asking why the other 4 points 2, 3, 6, and 7 are not matched with points 1 and 5 and determine lines of the geometry. For such points such as 1, there are 3 lines of geometry on it. These contain the other 6 points of geometry, 2 on each line. None of the pairs of points on one of these lines can be matched with a point on another line without contradicting axiom 4. For the concept of parallelism, this is not evidence in Fano's geometry since pair of lines has a point in common. On the other hand, it would be quite possible to give a new interpretation of parallel for this finite geometry so that the concept could be considered in a way quite different from that used in Euclidean geometry. Example, using the diagram, suppose that any 2 lines intersecting in line 4, 7, 3 are called parallel in Fano's geometry. Then, lines 5, 2, 7, and 1, 6, 7, for example, are parallel in this interpretation since they have point 7 on 4, 7, 3 in common. This example helps to emphasize the important role of arbitrary definitions in determining the structure of geometry. Let's move to the finite geometry of Young. Here are some of the old facts about Young. Young was born in 1773 in Somerset, England. He was a very intelligent child, learning to read at age 2. In 1793, he studied medicine in London and became a physician. He moved on to studying light, introduced the original theory of color. In 1816, he helped ascertain the precise length of the seconds or seconds pendulum. He was one of the first to try deciphering Egyptian hieroglyphs by studying the Rosetta Stone. He is also the first to define energy in scientific terms. His description of elasticity came to be known as Young's modulus, and he is also one who established a finite geometry. The finite geometry of Young is a different finite geometry obtained from Fano's geometry by a modification of the last axiom. It has the first 4 axioms of Fano's geometry along with a substitute axiom for axiom 5. Here are the axioms for Young's geometry. 1. There exists at least one line. 2. Every line of the geometry has exactly 3 points on it. 3. Not all points of the geometry are on the same line. 4. For two distinct points, there exists only one line on both of them. And the substitute number 5, if a point does not lie on a given line, then there exists exactly one line on that point that does not intersect the given line. Let's proceed in theorems in Young's geometry. Theorem 1. For every point, there is a line not on that point. Theorem 2. For every point, there are exactly 4 lines on that point. Theorem 3. Each line is parallel to exactly 2 lines. Theorem 4. There are 3 lines, no 2 of which intersect. Theorem 5. There are exactly 12 lines. And Theorem 6. There are exactly 9 points. Therefore, the finite geometry of Young, as seen in its configuration, is a finite geometry of 9 points and 12 lines. Let's now move to the finite geometries of Pappus and Desargues. Pappus of Alexandria lived in 340 AD. He has the Theorem 1.9, or what we called Theorem of Pappus. It says that if A, B, and C are 3 distinct points on one line, and if A prime, B prime, and C prime are 3 different distinct points on a second line, then the intersections of line A, C prime, and line C, A prime, line A, B prime, and line B, A prime, and line B, C prime, and line C, B prime are collinear. Let's now take a look at the Pappus theorem configuration, which states if points A, B, and C are on one line, and A prime, B prime, and C prime are on another line, then the points of intersection of the lines A, B prime, and B, A prime, the lines of intersection of the lines A, C prime, C, A prime, and the lines of intersection of the lines B, C prime, and C, B prime lie on a common line called the Pappus line of the configuration. Looking at the configuration, we can say that the Pappus geometry configuration has 9 points and 9 lines. Here are the axioms for Pappus geometry. 1. There exists at least one line. 2. Every line of the geometry has exactly 3 points on it. 3. Not all points of the geometry are on the same line. 4. There exists exactly one line through a point not on a line that is parallel to the given line. 5. If P is on a point not on a line, there exists exactly one point P prime on the line, such that no line joins P and P prime. And 6. With the exception in axiom 5, if P and Q are distinct points, then exactly one line contains both of them. Theorem 1.10 says Each point in the geometry of Pappus lies on exactly 3 lines. Next, point or line duality. If you have any diagram of points and lines, you can replace every point with coordinates A, B, C with the line coordinates A, B, C, and vice versa, and you still have a valid diagram. If you do this to Pappus theorem, you get another version called the dual version of Pappus theorem. So, let's take a look at the Pappus theorem, the dual formulation. Let us pick any 2 points. Through each, draw a red line, a blue line, and a green line. Next, let us find the intersection of the lines of different color. Next thing, draw the lines that connects the 2 red-blue crossing, the 2 red-green crossing, and the 2 blue-green crossing. Now, this completes our dual formulation, and these lines are coincident. In Pappus theorem, original and dual. In original, we draw 2 lines with red, blue, and green points. Draw the lines connecting points of different colors. Find the intersections of the 2 red-blue, the 2 red-green, and the 2 blue-green lines. These points are collinear. In dual, draw 2 points with red, blue, and green lines. Find the intersection of lines of different colors. Next, draw the lines connecting the 2 red-blue, the 2 red-green, and the 2 blue-green points. And these lines are coincident. Next is the Desargues finite geometry. We have Gerard Desargues, who lived in 1591 to 1661. He is known as the father of projective geometry. In Desargues Theorem 1 states that 2 triangles are said to be perspective from a point if 3 lines joining vertices of the triangles meet at a corresponding common point called the center or polar point. This is the illustration in Desargues Theorem number 1, where there are 2 triangles which are said to be perspective from a point which 3 lines joining vertices of the triangles meet at a corresponding common point called the center or polar point. And this triangle is said to be perspective from a point. In Desargues Theorem number 2, it focuses on line perspective, which states that 2 triangles are said to be perspective from a line if 3 points of intersection of corresponding lines all lie on a common line called the axis. So, we can say that these two triangles are said to be perspective from a line. In Desargues' theorem number 3, Desargues' theorem states that two triangles are perspective from a point if and only if they are perspective from a line, just like the configuration shown. Therefore, from Desargues' theorem number 3, the Desargues geometry configuration has 10 points and 10 lines. And for the other finite geometries, Fano's finite geometry has the special property of being self-dual. In other words, the plane dual of each true statement is a true statement for the geometry. Actually, Fano discussed a particular set of finite geometries, each of which was self-dual. The general symbol for geometries of this special type is PG, coordinates NQ. The letters PG stands for projective geometry. The letter N is the number of dimensions, and Q is the positive integral power of a prime number. The geometry has Q plus 1 points on each line. Thus, Fano's geometry of the plane is PG with coordinates 2, 2. Since there are 3 points on each line, the theory of projective geometry can be used to establish the following useful theorem assumed here. The Theorem 1.13, which is the general formula for the total number of points in PG with coordinates NQ, is Q raised to the power n plus 1 subtract 2, 1 all over Q minus 1. Let's have one more glance to the leading figures with their work in the finite geometry. We have Gino Fano for Fano's geometry with this configuration, which shows that it has 7 points and 7 lines. Next is Yang in his Yang's geometry with his configuration, which shows that it has 9 points and 12 lines. Next is Pappus with his configuration, which shows 9 points and 9 lines. And lastly, Desargues with his configuration, which shows that it has 10 points and 10 lines. With the work of those leading figures in finite geometry, they truly made it to be the world's necessity, and so intimately linked with experimental design, information security, particle physics, and coding theory. Apart from being an exciting and interesting areas in combinatorics, finite geometry has many applications to algebraic geometry, group theory, codes, graphs, and designs. That ends our report. Thank you for listening.